Welcome to our cosmic journey on what came before the Big Bang. Today, we're diving into one of the universe's greatest mysteries, the origins of everything. Scientists and theorists have long debated what existed before our universe exploded into being. Was it an infinite void, a previous universe collapsing in on itself, or something entirely beyond our current understanding? Join us as we explore the intriguing theories and evidence that aim to answer this mind-bending question. Fasten your seatbelts, and we're about to take a trip through time to the very beginning. Or perhaps to what was before the beginning. Quantum fluctuations are akin to the unexpected popping of bubbles in a still glass of water where, instead of bubbles, tiny particles appear and vanish in what we think of as empty space. This theory suggests that nothingness isn't empty but a stage for a ceaseless dance of particles coming into and out of existence. This invisible ballet is not just a theoretical fancy, it's a fundamental aspect of the universe, hinting at the vibrant activity hidden within the vacuum of space. One of the most striking pieces of evidence for quantum fluctuations is the Calimero effect. Imagine placing two mirrors facing each other in a completely dark room. According to classical physics, nothing should happen because there's nothing between them. However, in the quantum world, these mirrors will move closer due to the pressure exerted by the light that isn't there, or more precisely, the quantum fluctuations of the vacuum between them. This effect has been experimentally observed, providing tangible proof of these fluctuations. The analogy of whispers in an empty room might help here. Just as whispers can suddenly arise and fade in a silent space, quantum fluctuations are the universe's way of murmuring secrets, revealing a layer of reality beyond our immediate perception. This insight into quantum fluctuations bridges the gap between the complex quantum realm and the everyday world, highlighting the profound and lively mystery of the vacuum. The multiverse theory is like imagining an infinite library where every book represents a different universe. Each book has its own story, with variations in characters, settings, and plots. In this vast library, our universe is just one book among countless others. This theory suggests that there are multiple, perhaps infinite, universes existing alongside ours, each with its distinct laws of physics, cosmic landscapes, and possibly even life forms. One intriguing piece of evidence supporting the multiverse theory comes from the cosmic microwave background, CMB, the afterglow of the Big Bang. Scientists have observed cold spots in the CMB that are difficult to explain within the framework of a single universe. These cold spots could potentially be the result of interactions between our universe and other universes, hinting at the existence of a multiverse. Imagine a bubble bath, where each bubble represents a universe. The bubbles are separate but share the same space and can sometimes affect each other. This analogy helps illustrate how our universe could be part of a much larger cosmos, a cosmic bubble bath, with each bubble following its own rules and containing its worlds. The multiverse theory expands our cosmic perspective, proposing a reality far more complex and diverse than we could have imagined. The pre-Big Bang universe theory is akin to imagining a book with chapters that precede the story's dramatic beginning. Rather than the first page marking the start of existence, this theory suggests there was a narrative already unfolding, a universe or state of reality before the explosive event we know as the Big Bang. This concept challenges the traditional view of the cosmos having a singular starting point, proposing instead that the Big Bang was merely a transition phase in a much larger cosmic saga. One compelling piece of evidence for this theory comes from the study of cosmic microwave background radiation, CMB, the afterglow of the Big Bang. Researchers have detected subtle irregularities in the CMB that are very difficult to explain solely by events following the Big Bang. These anomalies could hint at physical processes or structures that existed before the Big Bang, suggesting a pre-existing universe or state of the cosmos. To make this idea more accessible, consider the analogy of a phoenix rising from ashes. Just as the mythical bird is reborn from its own demise, the pre-Big Bang universe theory posits that our universe could have emerged from the remnants of a previous cosmic cycle. This perspective invites us to view the universe not as a one-time occurrence, but as part of an eternal cycle of birth, death, and rebirth, expanding our understanding of cosmic history. The Ekpyrotic Universe theory is like imagining two giant sheets of paper floating in an infinite space, slowly moving towards each other. These sheets represent branes, or dimensions, in string theory. When they collide, the impact generates a massive burst of energy, akin to a new Big Bang, giving birth to a universe. This theory proposes that our universe's beginning was the result of such a collision, challenging traditional views of the Big Bang as the universe's singular commencement. One piece of evidence supporting the Ekpyrotic Universe theory is the uniformity of the cosmic microwave background, CMB radiation, combined with the existence of slight irregularities. This theory offers a compelling explanation for these observations, suggesting that the high-energy collision between brains could lead to the smooth and evenly distributed universe we observe today, punctuated by small anisotropies. Imagine two clapping hands as an analogy. Just as the clap creates a sound wave, the collision between two brains in the Ekpyrotic model generates waves of energy that form the universe. This collision sets the stage for everything we see around us, from galaxies to the tiniest particles, offering a fascinating alternative to traditional Big Bang models and inviting us to rethink our universe's origins. The no-boundary proposal, conceived by Stephen Hawking and James Hartlett, is a fascinating concept that reimagines the origins of our universe. Instead of picturing the universe starting with a Big Bang from a singular point, this theory suggests that the universe, like the Earth's surface, doesn't have a boundary or edge. Imagine setting out to find the edge of the world only to discover that you can keep going forever because the Earth is round. Similarly, the no-boundary proposal posits that time and space are finite but unbounded, seamlessly curving back on themselves. A piece of evidence supporting this theory comes from the way the universe appears to be finely tuned for life, which could be naturally explained if the universe has no boundaries, thereby avoiding the need for a beginning with specific initial conditions. The proposal aligns with observations of the cosmic microwave background radiation, which shows a uniformity consistent with a universe that smoothly emerged from a boundaryless state. To make this easier to grasp, consider a video game on a spherical world where you can move in any direction without ever hitting a wall. The universe, in this analogy, operates on a similar principle, with space-time curved in such a way that you can never find an end. This theory revolutionizes our understanding of the cosmos by suggesting that the universe itself is a closed loop, with no start or end, just an infinite continuation. Eternal inflation is a captivating theory that extends the concept of cosmic inflation, suggesting that the rapid expansion of the universe after the Big Bang never truly stopped. Instead, it continues in various regions, giving rise to an endless creation of new universes within a vast cosmic multiverse. Imagine blowing bubbles in a park. Each bubble represents a universe. While some bubbles pop, end, others keep forming and expanding, creating a never-ending process of universe generation. The strongest evidence supporting eternal inflation comes from the observed uniformity and flatness of the universe, which is precisely predicted by inflationary models. Inflation explains these features by stretching any initial irregularities, leading to the smooth, homogeneous cosmos we observe today. Additionally, quantum fluctuations during inflation could trigger the formation of new regions of space that themselves undergo inflation, perpetuating the cycle. To visualize, think of a garden where flowers bloom continuously in different areas. Some flowers may wilt, universes that end, but new ones are always budding, new universes forming, driven by the underlying ongoing process of growth, inflation. This analogy helps illustrate how eternal inflation proposes a cosmos where the creation of universes is a constant dynamic process, offering an endless landscape of possibilities. And that wraps up our exploration into the enigmatic question, what came before the Big Bang? From the infinite loops of cyclic universes to the boundless landscapes of the multiverse, we've journeyed through some of the most fascinating theories that science has to offer. While the true answer remains shrouded in the cosmic unknown, the quest for understanding pushes us closer to unraveling the mysteries of our universe's origins. Thank you for joining us on this celestial adventure. Don't forget to like, share, and subscribe for more cosmic journeys. Until next time, keep looking up and wondering about the wonders beyond our world.